Well, this question too, I actually used the central limit theorem to find the sample mean, actually the average weight in this question higher than 167. So from the central limit theorem, we know that, well, the original weight is normally distributed, therefore the sample mean also follows the normal distribution. And from the sampling distribution, we know that sample mean has a mean of 172, same as the population sample standard deviation. Population standard deviation of the sample mean follows the population standard deviation over square root of n, depending on the original population standard deviation and depending on the size. Right, so that is the application and the wording how we use the central limit theorem. Right, the first question was usually the normal distribution question. The second one is using the central limit theorem to ask the question. Right, so let's see the next example. The volume of 12-ounce Coke known to have the mean volume of 12.00 ounce and standard deviation of 0.11 ounce. Or especially we see we didn't mention that the volume is normally distributed. We don't know if it's normal or not. It didn't say anything about the normal at all. Right? So the body sample. Right, so we found a sample of 36 cans of Coke and has a sample mean volume of 12.19 ounce. Right, so it's usually or sometimes happened that you use the machine to fill in or fill up the Coke cans, right? But as time passing, right, the volume controlling may be a little trouble, right? So in this case, we got 36 cans and to have a sample mean more than 12.19 ounce. So the question we can ask is, well, is that usual, right? Is that a usual case? That if the machine set 12 ounce was it's supposed to be set, if the machine is actually follow that idea, right? Follow that rule or follow that original setting, right? Is that possible to get, or is that usual to get 12.19 ounce? Or we can conclude that if unusual, we may say, well, some trouble with the setting of the machine, right? Something wrong with the machine could be, right? I find that, well, find the probability of getting 36 cans of Coke will have a mean volume of 12.19 ounce or greater. We'll do the result. If we say the probability to getting that cans is very unlikely, assuming the average mean volume for 12 ounce Coke filling is 12 and the standard deviation of 0.11, is that usual to get 12.19, right? If it's unusual, that means the original setting was maybe a little not correct, right? So let's see. Alright, the sample mean is 12.19. As get from the 36 cans, right? So we get the mean was 12 ounce and the standard deviation is 0.11 ounce and the size was 36. From the central limit theorem or from the sampling distribution, we know that the mean of the 36 cans should be 12 and the variance should be 0.11 divided by radical 36. That is 0.018333 and more. How we know the sample mean follows a normal distribution or can be approximated as normal distribution is because even though we don't know how much it is or how many, even though we don't know it is normally distributed, but the sample size is more than 30. We get 36 as the sample size. Therefore, we can see the sample mean as approximated by a normal distribution. And then the z-score for the sample mean is the z minus the mean of the sample mean over the standard deviation of the sample mean. Right, the more digits we keep, the more accurate the answer we get. And we get 10.36 as the z-score. So we're able to find probability for sample mean to be bigger than 12.19 to that probability was asking, greater than or equal, same thing. Well, mean volume of 12.919 ounce or more. That is same as finding the probability of the z-score is 10.36 or more. One minus the table value of 10.36, and for the extreme value from the table, we can see, right, either the negative and positive side. The negative side say negative 3.50 and the less, that we use 0.0001 as the probability. Any value smaller than 3.5 is the same. And for the positive side, we say anything bigger than or equal 3.50, and as we see on the bottom, we use 0.9999. Of course, the true value will be much bigger than 0.9999, but that is the table we get. So just follow the idea. So we get the value of the probability, right? The probability of getting 36 cans of Coke will have a mean volume of 12 ounces or greater is only 0.1%. So it is very unusual to get 12.19 as the volume on average of the Coke as the sample if the basic condition we make is the mean is 12 ounce and standard deviation is 0.11 ounce. Right, so if we follow the idea that the machine to fill up the Coke is working properly as was being set before to be 12.00 ounce, that means it is very unusual to get 12.19. Right, so one case could be we are very lucky to get the 12.19 ounce, but that is very, very unusual, very, very unusual to get that point 12.19, which means to get very lucky is not that usual. Right, like winning the lottery, the first place is not that very likely to happen. Right? Then, if that is usual, I mean, if in other words, if to get the sample is nothing wrong with it, right? The sample is random enough to get that 36 can. The only thing can be making mistake is the population mean, which means the machine filling in may not be 12 ounce no more, right? So it was 12 ounce, but as time passing, the machine was like is no more that much accurate. Right? Maybe every time it fills in will be a little bit greater than 12 ounce to put in. Maybe it is 12.1 ounce or 12.15 ounce to get that Coke average volume. So do the results suggest that that Coke cans are filled with amount greater than 12 ounce? Yes. It suggests the Coke can filled with an amount greater than 12 ounce. It suggests that because it is unusual to get 12.19 ounce if the mean was 12 ounce. It must be bigger than 12 ounce that we are able to get this volume of 12.19 ounce of the 36 cans of Coke. Right, so that is the different way can be asked for the central limit theorem. But to ask usual or unusual, and the suggestion is only suggestion. Right? It is very, even though it's very unlikely to happen that we are very lucky to get the 12.19 ounce of Coke from the mean is filled in to be 12 ounce, but that still happens, right? Still able to happen. Like, where someone's still able to win the lottery, even though that is very, very low likely, with very, very low likelihood. Right, but that is the idea, right? We have seen before, if someone is unlikely to happen, then maybe the condition we had set before is a little wrong, right? By time passing, it could be the machine could be not working that well. It is a likelihood, it is a possibility, right, of that thing could happen. So that is the central limit theorem anyway. The key thing here, even though we don't know the population or the distribution of the original population, right, but the size is big enough, as we see more than 30, right, then we can use the central limit theorem to approximate the sample mean in a normal distribution. Right? Then this thing always holds. These things, the mean of the sample mean, the standard deviation of the sample mean, those formula always holds. Doesn't matter if it's normal or no. Right? The only thing is, if it's not normal, we cannot use z-score to approximate. Right here, we can use it to approximate because the size is big enough. Right? So we'll see some other approximation next time. This is about normal distribution and the central limit theorem. We'll see more. Another thing is that the binomial distribution could be approximated by the normal distribution. I will see that next time.